Hi, it's Robin. You might know it's fun to play around with the border on the C64. Poke 53280, 0. We'll turn the border black, 1 turns it white, 2 turns it red. It's a favorite thing for a lot of Commodore 64 coders, as it's a very easy way to show a program is still working without really affecting the main screen, and it does something very noticeable just by playing around with a single memory location. It's making good use of that otherwise unused space around the screen. Now, in a previous video, I showed how to disable or remove the top and bottom borders and display sprites in that area that's usually covered. It's also possible to remove or open the side borders as well, but it's a lot trickier, and while I have coded that before many years ago, I haven't made a video about that, and I'm not going to today. Instead, we're going to do sort of the opposite thing. Instead of getting rid of the border, let's make it so the border covers the whole display. It's a feature built into the video chip. All you have to do is poke 53265, peek 53265. At least this is one way of doing it. And 255 minus 16. And what this does is takes the current value of that register, and by ANDing it with 255 minus 16, we are turning off bit 4. This is 2 to the power of 4. And what this does is makes the border cover the whole screen. So here we go. There you go. Now the whole screen is just filled with whatever color is specified in that border color register. It's almost like the whole screen is a single giant pixel. Now, this is really what old school graphics are all about. Like I tell my kids, back in my day, we only had 1 pixel on our computers, and we learned to be happy with that. So we can change the color of our giant screen-sized pixel by blindly typing poke 53280, and I'll do 1. So we change the border color to white, or poke 53280, 4 should make it purple. Yep, there it is. Okay, so to get out of this, we could try doing that poke 53265 blind, but that seems like a pain. Instead, hold down stop and tap restore, and that resets the video chip registers. Rather than doing the peek and the and then the poke, which in a way is good practice because it preserves the other bits in that register, we can just do a shorter poke 53265, 11. So now the border is extended over the screen, light blue, and it's easier to type in this blind 53265, 27, which is the default value. And again, you see this is what the VIC chip is normally initialized to at power up, 27, and 16 less, again, 2 to the power of 4 to clear bit 4, which is what controls this border effect. So that's easier to type in blind. Okay, now I suppose I'll admit that giant pixel isn't very useful, but we can actually use this to better understand some aspects of how the C64's CPU and video chip work in sync. So today we're going to try a couple things that I hope you find interesting and educational. I found it interesting anyway. This video isn't turning out exactly the way I planned originally. As I was playing around with this idea, I kept going in different directions because I was seeing interesting things. So in a way, this video is just going to be a bunch of kind of related facts and demonstrations, and I hope all of it will start to make these things make more sense to you. At least that's how it worked for me. Sometimes science is messy. Okay, so today I've got my Kung Fu Flash, and it's running the Super Snapshot ROM. Here, I'm just going to reset. Down the bottom corner, this is Adrian Gonzalez's modified Super Snapshot ROM. You see it says version 5.34 NTSC. And actually, I'll probably even be using it on my PAL machines. I think it only matters when you're talking to real Commodore 1541 disk drives or other old school disk drives that are timing sensitive. It seems the SD to IEC that I'm using back here really doesn't care. I guess it's generous with its timing. And the PAL NTSC difference doesn't really matter. Okay, I've got a D64 image called border.d64. And I'll probably include a link to a download for that. Might have a mess of files on it. When it's necessary, I'll explain what file I'm using. Okay, there's the files on this copy right now. By the time you download it, it might be a little bit different. And to load Turbo Macro Pro, you can either load COM8, 1 or just with Super Snapshot, the percentage sign. And we will do an SYS 32768 to start up Turbo Macro Pro. And for the rest of the video, I'll skip over that step, even though I've probably ended up doing it a dozen times by the time I'm done recording this video. Okay, so I'll load up a short program I have here called Border 1. And I'll just explain it here. Temp equals 8000. That's for Turbo Macro Pro is located at location 8000 hex. That'll matter in a moment. We're going to assemble to location 1000 hex, and I just arbitrarily chose that. Now this little trick I've shown before, but just to explain it again for anybody new, all we're doing is setting the NMI, the non-maskable interrupt vector, to point to Turbo Macro Pro, this assembler we're using. And this is kind of like a little hack or trick. When you tap the restore key on the C64, it triggers an NMI, a non-maskable interrupt, and it jumps this location. And unless you're using the restore key for some other function, this is a really nice way of being able to re-enter our assembler very quickly. Single key back to it. So we're just pointing the low byte and the high byte in the corresponding vector location. Okay, then we're going to just disable interrupts, disabling the kernel interrupt that scans the keyboard and so on, because that would interfere with the timing of our program. Because the restore key doesn't require that key scan, it still works. It's literally directly wired into the NMI pin on the CPU. It's kind of hilarious. All this is doing is that poke 53265, well, that's D011 in hex. And this is just the equivalent of putting that value of 11 in this VIC control register, which makes the border the full screen. Then all we're going to do is load the accumulator with the value 2, which is the color red, store it in the border color. D020 hex is the same as that 53280 that we were playing with in BASIC. And then we're going to jump back to loop. So it's just an endless loop storing the color red in the border. Okay, so let's see what that looks like. Back arrow 3 to assemble, and we'll start the program. I guess that's what you'd expect. The screen is completely red. Okay, but this is where we're going to learn about a quirk. Okay, now I've switched over to the Commodore 64C that I use in many of my videos. And this is where we're storing red in the border color repeatedly, and that looked fine on my old breadbin C64. But here, look what it does on this. Back arrow 3, start. Instead of just being a nice solid red, as red as the C64 gets, it's got this pattern of dots, which at least to me is looking like it's scrolling slowly up the screen. Now that's just kind of an illusion. There's a pattern going on here, and over time it looks like a scrolling animation to us. But it's not really doing a deliberate scrolling. It's just a pattern that happens to line up. Just because it's a repeating pattern, if it moves, our eyes will take it as an animation. But what this is showing is sort of a bug or a glitch in the newer VIC-II chips that the 64C has, and the Commodore 128, I believe, also has this. That is, repeated writes to a color register, especially one noticeable like the screen or the border, will cause this little pixel glitch, almost like a spark, to appear. Certain commercial games actually had this because they were coded on older C64s, and when they came out new, you might notice where there's like otherwise a nice black screen with some smooth scrolling effects or something, and there'll be some glitchy little pixels here and there. That's because of this, we'll call it a hardware bug. Repeated writes to the same location cause this little spark. In fact, I guess it's actually happening even if you're not putting the same value in, but it's not nearly as noticeable because you're expecting the color to change there. If there happens to be a little white pixel in there, it's not such a big deal. Okay, so if I hit restore, you see the problem here is that we're putting the same value repeatedly. So an easy way to fix that is to just move loop down here, so when the jump happens, it doesn't keep putting that value unnecessarily in D020. Or if you're writing a more complicated program, like any program that's more complicated than this, you just have to avoid putting the same value in the register over and over again. Back arrow and 3, and there, it's fixed. Okay, I probably also didn't explain very well. The reason the dots are covering the screen is that the screen is being drawn top left to bottom right, and as the CPU is ticking along, incrementing, it's just busy doing that increment and jump, the screen's being drawn. So it's whatever part of the screen's being drawn at that moment that the ink happens, that these little dots will appear. And it's just the math of it, the timing of it, that makes it look like this animation. I think this will become a little bit more clear later. Okay, and back to this breadbin. Isn't it gorgeous? It has like the VIC-20 keys. This is from the factory this way. Okay, so we're going to make just one change to this program. Instead of repeatedly storing the same value in D020, we're going to increment D020, and that's the border. The CPU will increment the value in that register, and it will just wrap around automatically. It'll go from 0 to 15, and then wrap around. There's only 4 bits that are active. Actually, it'll be the disconnected bits are all F. So really, it'll go from like value 240 decimal to 255 decimal, and then wrap around, or in hex, F0 through FF, and then wrap around over and over again. It just does that automatically. Okay, so let's see what it's doing now. Back arrow 3, and we'll start it. Okay, and this might be flashy. If you really are sensitive to flashing screens, I better warn you. That might happen on and off during today's video. Okay, so we've started it, and we get this really wild pattern. And if it looks to you like it does to me, it actually depends where I look on the screen. Either it looks like a whole bunch of diagonal lines running up and to the right, or there's also another pattern that looks like bigger blocks scrolling up and to the left. I don't know if that's an optical illusion or something. It depends how I focus my eyes. I hope that effect will still come across in the video. But what's going on here? I can't do this on my real C64, but in my video editing software, I can pause the video and I'll try and zoom in. And I hope I'm going to describe this right, because I can't actually see it for myself right now. And so the screen is drawn from the top left corner, horizontally to the right, one scan line. Then it goes to the next scan line, draws from left to right, all the way down. Now, on an NTSC machine, it does 263 scan lines like that. And on PAL, it does 312, but that's at 50 hertz, 50 frames per second. But no matter what, they all draw from the top left, one line at a time, from left to right, over and over again. Okay, so it's a repeating pattern, but it looks kind of chaotic. If we locate a black line, that is color 0. And if we look immediately to the right of it, we should see white, which is color 1. Then we should see color 2, which is red. Then we should see cyan, color 3, and then purple and green. But sometime around now, we're going to run out of horizontal space on the screen. There is an exact match between CPU cycles and pixels on the screen. Every one CPU cycle is 8 pixels horizontally on screen, or let's just talk about them as characters. because there are 8 pixels to a character. We have a 40 column screen on the Commodore 64. 40 columns takes 40 CPU cycles. An NTSC machine has 65 cycles across the screen, but not all of them are visible. And it will vary a bit from monitor to monitor and so on, but we're going to have somewhere around 40 characters of the actual visible typable screen, and then the borders are going to be, say, 3, 4, 5 characters worth each. And so your total visible screen, including the border, is going to be somewhere around 48, 50 characters. And I said there's 65 across, so there's going to be about 15 off to, you could imagine it to the right or the left, it doesn't really matter, that are invisible. The computer is still ticking those out, but during that time, at least on old school CRT, the raster beam was actually wrapping back around. It's called the horizontal blank. Okay, so if we keep, there's lots of explanation going on here, not a lot changing on the screen. If I'm using an arrow or whatever to show it, the CPU is still changing that color register, but some of it's going to be off the screen in the borders, and then the next line's going to start coming along, and then we'll see where it's gotten to at that point. So maybe we're going to miss the green and the blue colors, and then yellow will show up. Basically, we're going to be going through the 16 colors. Then once we get near the end, we get to the dark gray, medium gray, light green, light blue, light gray, and then it's going to wrap around. Light gray is color 15. It'll wrap back to 0, as we discussed, and that'll be black again. And then that pattern repeats. Now, why is it all kind of staggered and so on? Okay, well, just to look back at the code for a moment, this is where cycle counting comes in. Increment D020 takes 6 cycles. Jump to loop takes 3 cycles. So this little loop is repeating every 9 cycles. Again, there's a direct relationship between these 9 CPU cycles. The border color should be the same for 9 characters worth. So if our screen is 65 and we divide that by 9, we're going to end up with 7 and a remainder of 2. So across a full 65 cycle line, you've got room for 7 color changes and 2 remainder. And of course, because that can be offset, that might mean you have 7 plus a little bit of 1, or it could even mean that you have 1 color for just 1 cycle, 7 color changes in the middle, and 1. And because of that horizontal blank area, somewhere around 8 of those at either end won't actually be visible. Okay, so I said that 65 cycles, and each of the color changes takes 9. Okay, so that's 7.2, well, I got 0.222, but that represents 2 cycles. Those 2 cycles are what's causing the offset. 2 cycles get drawn in here, so therefore the next line, they're to the left, and that's what's causing these diagonal effects. It doesn't work out, what did I say, 263 times 65, 1,795 machine cycles per frame. And if we try to divide that, say, by 9, it's not an exact number of border color changes per frame. Therefore, it's not going to look stable at all. Our code isn't syncing to the video display at all. So any animation or any effect that we see is kind of just coincidence. It has to do with the repeating pattern and how we pick up on patterns as they shift about. Okay, but that loop happens to take 9 cycles. Well, 9 times that same 7 is 63 cycles. That just happens to be how many cycles are on a PAL Commodore 64. 63 cycles per line. So I'm going to switch to that. Okay, here's the Swedish C64. Thanks to Magervalp. Okay, exactly the same code we were just looking at. But let's see how it reacts on the PAL C64. Back arrow 3, start. And instead of a wildly scrolling screen, we get this incredibly stable image. So why the difference? Exactly the same code, very different looking results. Okay, so each of these color bar changes, you see how we have these vertical stripes? Well, each of them is 9 characters wide. Again, that loop is 9 cycles. And I can see 1, 2, 3, 4, 5, and a little bit of 1. So I think we're seeing 5 full ones, although that right-hand one, maybe we're missing 1 character there. And maybe we have, 3 on the left. Sorry, it's hard for me to know exactly. I'm just kind of estimating here. I don't have the basic editor active. I can't cursor around and measure it. But I think what we have here is 5 rows and then plus 2. So I think we have 9 times 5 is 45 plus 2 or 3. I think we'll say around 47 characters visible. And the whole line is 63, which divides evenly by 9 into 7. We're not seeing one full color change, and we're just seeing part of a second one. We have horizontal stability because 63 cycles can be exactly divided by 9. So that's why we have this horizontal stability, that the border color changes are happening at exactly the same place on each horizontal line. I probably haven't made a very big deal about that, how again, this is just our one giant pixel, but we're changing it on the fly, and those changes, we can see them, and because they're happening with regularity, we perceive it as a still image. Okay, so the horizontal stability. Why is there vertical stability? Well, it's because they have 16 different colors, and I suppose coincidentally, the math just works out this way. Let's do a little math in BASIC. PAL has 312 scan lines per frame, and across each scan line, we're doing exactly 7 border color changes. And that equals 2,184. This is experimental, guys. It's science. I thought we were going to find that 16 went in with no remainder, so that over the course of a frame, if you happen to start with corner 0 up in the top left corner, that because of the number of border color changes, that by the time it got down to the bottom right corner, it would just flip back to 0 exactly the right moment. That's why it looks stable. But instead, it seems that every second frame is going to flip back to 0. So it's going to be color 0 on one frame, then on the next, it's going to be color 8, and then on the next, it'll be back to 0 again. It's flickering the two at half time and creating a stable flicker color. So I'm back on the classic breadbin. Okay, so I've got source 2 loaded up here. Looks like I forgot to put the NMI shortcut in this one, but that's okay. So all we're doing is disabling interrupts, shrinking the border, and this time instead we're taking color 2, putting it in D020, and then we're going to increment D020 several times. And then there's this knob. I'll explain that more later, and then we'll jump back up to loop. So let's just try and look at back arrow 3, S. Okay, so this time, this is very similar code, except now we've got these nice, stable, horizontal bars. There's a few things to actually talk about here. Take note of where red is right now, and then there's the cyan and purple and so on beside it. We'll talk about that part first. So just note where red is. You just restart the program like this, 4096. That's 1000 hex. Okay, so now this time red is way over there at the right. Oh, isn't that funny? Actually, wasn't expecting that. Okay, so each time we hit restore, just keep an eye on red, eh? Well, it's almost like it's doing a predictable scroll to the left. Okay, so the NMI vector must still be running. It's just wasting a bit of time. Very interesting. Okay, this is yet more science here. So if I hold down stop and restore, yeah, it does drop us out. Okay, let's explain some of this. So we'll go into Turbo Macro Pro. The reason I was having you watch red is that's the color that we're defining first here. I'm loading accumulator with 2, that's red, and putting it in D020. And then there's a pattern that starts here, and then we jump back up to loop, and again, we load A with 2. I guess that isn't necessary. Well, it is because of the timing. The important thing here is that red is where our logic is beginning. But as we've seen, red can be on different parts of the screen. Sometimes it's even off the screen altogether. Okay, can you think of why that is? It's because as the screen is being drawn left to right, our code doesn't know where the raster currently is. That's kind of like an independent operation of the video chip. And there are ways of trying to sync up to that, but we're not doing that. So therefore, every time we run the code, it's just kind of random. It's not all random. It's all super deterministic. But from our perspective, we don't know where red is going to be on the screen. We're not in sync with the starting position of the video. Red might be anywhere from the very first. We've talked about how there's 65 cycles, again, NTSC, 65 cycles across the screen. Red could start at cycle 0, 1, 2, 3, 4, all the way up to 64. So sometimes it's not even on the screen. It might be in the borders, whatever. But once we start drawing red at whatever position we end up in, at whatever X position, it's a solid bar down the screen because we're repeatedly doing the same thing in sync with the horizontal scan. And why is that? Okay, load A is 2. I hope I do this right. Okay, so that's 2 cycles. Storing it is 4 cycles. We're at 6 altogether. Increment, that is 6. And each of these is 6 cycles. And then that NOP is 2. And that jump is 3. Okay, so this is, those two together are 6. This is 6. So we're going to count 6s. 2, 3, 4, 5, 6, 7, 8, 9, 10 6s is 60 cycles. Plus 2, plus 3, 65. So this block of code here takes exactly 65 cycles over and over and over again. So the background register is being changed at precisely the right intervals that all lines up as if we have these vertical columns down the screen. And again, this is our one giant border color pixel, but you see that is a misnomer. You might think, wow, it's only one register, but look at this display we're creating with it. And that's the concept of this on-the-fly programming, racing the beam, as it's called in the Atari 2600 circles. Well, the Commodore 64 is very capable of doing that too. Oh yeah, and the one other thing I want to say, yeah, each time I hit restore, it is running the kernel NMI handler, and that takes some number of cycles, and during that time, our code isn't running anymore. So I tap that, it goes and executes some kernel code, it returns back to our program, and then our code resumes drawing. And so that's why I think it's jumping to a pretty consistent value to the left each time. But again, it's just wherever our code picks up again, then it becomes a stable picture. You can even see a little flash on the screen when I hit restore, at least I can see it. And it's like several scan lines, so it's probably, I'm just guessing, that looks like about 6, 7 scan lines, probably about 300-400 cycles that it takes to process that NMI key. That's it running on a breadbin. Okay, so I've got source 2 now loaded up on my Commodore 64C with that newer VIC, and let's see what it does when we run this. Back arrow 3, start. Okay, it's essentially the same display, but there's an ugly line through, near the right-hand side of each one. Well, it's the same as that kind of extra white pixel that's output. You can sometimes see that line at the border, like between the pink and the gray there, or better yet, the dark gray and the red. You can see that line. It is ugly and distracting, but what's really bad is if you look on the pink or the brown, the blue or whatever, how one character to the left of the color change is a separate line. And those are especially ugly, and that is the bug really at work. Whoops. And this is due to a quirk of the increment command in the 6502, 6510. It actually does 2 writes to that register just as part of the CPU. It's like clockwork. Eh? The 6502 is amazing at how much it could do for so cheap. It changed the world. But it's not like a perfect CPU. And one of the quirks of it is that as part of the way it does the increment, it actually writes the same value twice. And that doesn't matter very much for RAM, like on 2 consecutive cycles. I'm not sure if they could have avoided this. I don't think I understand the design of the CPU well enough to know that. Maybe they could have avoided it, but that is what's happening. It's not incrementing it twice. I want to make that clear. The value is only incremented once. The old value is written into that register once, and then the new value is written in. And that's just part of how the increment works. Maybe if I understand it better one day, I can make a video just about those sort of very esoteric subjects. But here's how we can see something so esoteric. You can visualize it. Finish that thought. If you're just writing to a RAM value, you don't really care if the old value is written in briefly and then to a new value. But when you're writing into these kind of I/O registers, with video, it probably doesn't ever matter except these visual artifacts. But you can understand how writing the old and then the new value to some kind of input-output chip might have bad effects. At least we should be aware of this effect. But on the other hand, maybe you should never be incrementing an I/O register. You should just independently track it in a RAM location and then store it. That's probably best practice anyway. Incrementing an I/O register is kind of a weird thing, but of course on something like a color register, it's like a fun thing to do. Well, this is how we learn. Okay, and back to this breadbin. It's one of those Calgary Olympic 64s. I love this thing. Okay, this time I think I'm loading up source 6. And I'm going to make one change here where I've got this store X. Instead, I'm going to store Y there. I don't think I'm using Y at all. So I'm just going to load Y with 2, so I have the red color there. Okay, so basically I load source 6. I made this one change about Y. I think this is the last one we're going to look at today. So again, just the Turbo Macro Pro hit restore thing. Set interrupt. We're loading Y with 2. That's going to be our color. Just to start with color red again. Again, blank the screen. What we're trying to do is get it so our red color is at the left more consistently, not all random all over the place. To horizontally sync your code. That's what is sometimes called a stable raster. And it's a way of syncing the CPU and the video display exactly, cycle precise. I don't think we're going to do it perfectly today. This needs its own video sometime when I 100% nail this. So I'm going to show you where it's at right now. Okay, basically, if it's on line FF, that is D012, is currently 255 decimal, and it increments, it doesn't actually increment the register, just increments that value. If it's 255, then it will be 0 once it's incremented. It will burn 55 cycles. I hope my math is right there. So if it can be on line FF here, for sure, waste 55 cycles, and then still be on line FF here. If it's not, it'll go back up here again. It'll keep trying until it can be on line FF at the beginning, line FF at the end, with 55 cycles burned in the middle. And that must mean that it is more or less perfectly at the beginning of the new line when it finally exits this loop. So it might be in this loop for quite a while. I wonder if it could be in this line for like forever, if it's really unlucky. That's the thing. I'm sorry. I'm showing this, and yet this is kind of important, but I want to do this, its own video about this. I just want to explain how I think it's working. And then finally, once control passes to loop, that should mean that the raster is exactly at the beginning of the next line, or at least exactly the same cycle, even if it's not cycle 0, maybe cycle 1 or 2 every time. There might be a chance here where this might execute forever, and then we'd have to do the math. I guess it would have to be, when you do the math, it would have to be like, it'd be possible for it to get in a state where it could never be correct. Moving on. If we got through that, we should be more or less at the same position every time. Now we're going to store Y, which again, way back up here, we set to 2. So it's going to store red in here, do a couple nops, and then it's going to increment D020 as many times as it can, then jump back to loop. Again, this should add up to 65 cycles, and let's see if it works. I start, okay, and we can see red at the left edge of the screen, and light red or pink at the right edge, about 2 characters worth. Okay, let's run this repeatedly, and see if that red is always there now. Yeah, there's red. Ah, okay, you see, there looks like there's 3 characters worth at the right side. Start again, red and pink. Okay, so I think we've got an almost stable raster. Remember a while ago, red would show up at all different X positions, but now it's consistently at the left. And that's what that sync code is doing. But I think there's a case where that pink isn't always there. See, it's narrower this time. Sometimes it's 3 and sometimes it's 2. So there's still a problem. We're off by 1 cycle now. Okay, so that we're going to have to solve that another time. But we've got almost a stable raster here. Oh boy. Well, I'm sorry that was such a meandering thing. I hope there was still stuff learned there. I'm learning too. Some of this I'd figured out like way back in the 90s or the very early 2000s, and I got away from this kind of C64 coding. I was interested in the demo scene. Well, I was sort of participating in it too. I was a bit of an outsider, but yeah, I mean, I learned a lot then, but I learned a lot of other things since in game, doing professional game development. Since then, I got much more into this whole disassembling and reverse engineering, fixing games, and that's the C64 programming field is so rich that you can specialize so intensely. And just because you're a good C64 programmer doesn't mean you'll be good at making games or making demos or writing disk routines or there's so many specialties even within Commodore programming. Even you could be a really good basic programmer, and that might not seem impressive to the awesome assembly demo guy, and yet it is still a skill set that he doesn't have, maybe. Okay, thanks very much for your support, and thanks for your patience with me. I actually spent a long time trying to pull this together, and this is what happened. Okay, thanks to my patron supporters. Thank you for watching, and we'll talk to you next time.
On the C64, location 53280 controls the color of the border, while 53281 controls the color of the screen. Poke a 0 in and the screen turns black. Poke a 1 in and it turns white. So easy and quick to make that change. Change the color, the screen will flash, but not in a uniform way. It depends on the raster scan.